Welcome back to Max with RP. We are going to continue with word problems involving maxima and minima. So look at this problem. Let's read the problem first. A rectangle is inscribed in a semicircle of radius capital R with one of its sides on the diameter. Find the dimensions of the rectangle so that its area is maximum. So we have a semicircle and a rectangle is inscribed in the semicircle. Okay, so that one of the sides of the rectangle is actually lying on the diameter of the semicircle. So what is given? It is the semicircle is of radius r. So if this is the center, the radius of the semicircle is r. So that means if I join here, this will be r. Okay, let the dimensions of the rectangle be x and y. Okay, so let us keep this as say y and this as x. Okay. In fact, I want to keep it as 2y because it will make my calculations easier. I can avoid division by 2. So this part of the rectangle is y. This part of the rectangle alone is y. R is the radius of the semicircle. Is it clear? R is the radius of the semicircle. The semicircle is fixed. Therefore, R is a constant. Inside a semicircle, you can inscribe several rectangles such that one of its sides will lie on the diameter of the semicircle, okay, and then its vertices are fixed on the semicircle, right? Now, there are infinitely many such rectangles. We want to find that rectangle whose area is maximum. So, let the dimensions of the rectangle be x and y. X and y are variables. Okay, and what is it that we need to maximize? Area of the rectangle. Area of the rectangle, we'll call it as A. Try to use the same letter that is used to specify whether it's area, volume, so that there is no confusion in your mind. So let A, since we are dealing with area, I'm going to call the function as A. And what is the area? Length into breadth, which is length is 2y and breadth is x. So area is 2xy. We want to maximize the area. We want to find that rectangle of all the rectangles that can be inscribed within the semicircle whose radius is capital R. We want to find the dimensions of that rectangle whose area is maximum. As you can see, A is a function of two variables x and y. Okay. So we have to always in all these problems, the first step is to identify what is a variable and a constant. Step 2, what is the function that you are going to maximize. Step 3, how to express one variable in terms of the other using the given data. Here if you look at the figure, there are certain things which are striking. Like you have a right angle triangle because an angle in a rectangle is 90. So capital R square is x square plus this is y square. So y square is equal to capital R square minus x square. So the area function, as you can see, is 2xy. Now, if A is maximum, A square is maximum. So, A square will be 4x square y square, which is 4x square into capital R square minus x square from 1. So, I have now expressed it in terms of the area function in terms of one variable x, because capital R is a constant. This capital A square, let me call it as small a. Okay. So, A equal to, or rather A of x is equal to 4x square R square minus x square. So, A of x is 4x square R square minus 4x power 4. Now, dA by dx is, this is a constant, so I have to keep it as it is. Differentiating 4x square will give me 8x minus differentiating this will give me 16x cube. The derivative of 4x power 4 is 16x cube. The derivative of 4x square R square is, R square being constant, keep it as it is. 4x square, if I differentiate, I will get 8x. I am equating it to 0 because I want to find the critical point. So, 8R square x is equal to 16x cube. X being a length, I can cancel. Okay, for say 8 will go in 16 2 times. R square will be x square, cancelling x. I can cancel x. Why? Because x is a length. It is not a, it can't be 0. So, R square is x square. If R square is x square, what is y square from 1? Substituting in 1, y square will be R square minus x square. Right? But R square is x square. I made some. This is 4x square R square. So, 4x square, if I differentiate, I get 8x. This is 16x cube. So, cancelling, 8 goes in, sorry, 2x, there's a 2 here. Okay, R square x is 2x cube. Cancelling off one x, R square is 2x square. So, 2x square minus x square gives me x square. Okay. So, y square equal to x square. Now, so y will be x. If y square is x square, y is x. Okay. So, when x is equal to y, the area function is maximum. Are you able to follow? We have to maximize the area of the find the dimensions of the rectangle so that the area is maximum. Okay, x must be y. Now, what is x? X is the width of the rectangle. What is the dimensions of the rectangle? X and 2x. Why? Because 2y is the length. So, length is 2y, breadth is x. So, the dimensions are x and 2x. And what is the value of x? You know that x is equal to, from here, R square equal to 2x square. So, x square is R square by 2. So, x is R by root 2. So, R by root 2, comma 2x, 2R by root 2 will be the dimensions of the rectangle in order to have maximum area. Are you able to follow? Now, for these dimensions of the rectangle, is the area really maximum? How will we justify that? We have only found the critical point and we have okay, use the critical point to find the values of x and y, right? Now we have to use a second derivative test. Now we have to use a second derivative test to find out about the sign of the second derivative to determine whether area is maximum or not. Okay, so let me use a different color. So now you have, what is the first derivative? dA by dx is the first derivative. What is the first derivative? 8 r square x minus 16x cube. So d square a by dx square will be, okay, so 8 when I differentiate this, what will I get? 8r square minus 3 into 16 is 48 x square. This is 8r square minus 48 into, what is x square? X square is r square by 2. So 8r square minus 24r square minus 16r square is less than 0. Therefore, A is maximum when at x equal to r by root 2. So A is maximum at x equal to r by root 2. So is it clear? So what is the algorithm that we are following? First, understand what is a constant and what is a variable. Here capital R is a constant. X and Y are variables. We are maximizing the area of the rectangle. So area of the rectangle will be, what will be the dimensions of the rectangle? X and 2y. So I am square A equal to 2y into x, which I am writing as 2xy. Squaring, because if A is maximum, then A square is also maximum. Calling A square as small a, I have differentiated. I have found r square equal to 2r square, from which I got x equal to r by root 2 from that. Now substituting for y, you get y square equal to x square or y equal to x. Therefore, the dimensions of the rectangle will be what? X and 2y, but y is x, so x and 2x. So r by root 2 and 2r by root 2, or r by root 2 and root 2r will be the dimensions of the rectangle in order for the area to be maximum. We have also justified this by finding d square a by dx square and proving that it is minus 16r square, which is less than 0. The second derivative is negative at a particular value of x. Then for that value of x, area is maximum. Is it clear? Now, a closed right circular cylinder has volume equal to 128 pi. So, what is a cylinder? Okay, its volume is given 128 pi centimeter cube. Okay. Now, what should be the radius of its base? So, let us take the radius of the base to be small r and let the height be h. Okay. Now, what should be the radius of the base so that the total surface area may be minimum? So, what is the total surface area of a cylinder? Total surface area of a cylinder, you know, lateral surface area is 2 pi r h. Okay. And then you have the top and the bottom, because it says it's closed. So, pi r square plus pi r square, which is 2 pi r square. So, this is surface area, so I'll call it as S. S is equal to 2 pi RH plus 2 pi r square. Now, given this volume, you can have infinitely many cylinders which will have this volume, but they will have different radii and height. but we want to find the dimensions of that whose area is minimum. Okay, so for that particular cylinder whose area is minimum, let us suppose the dimensions are R and H. So both R and H are variables. R and H are variables. So the first step is to identify what is a constant and what is a variable. Volume is a constant. Okay. Now, if the volume is, what is the volume of a cylinder? Volume of a cylinder, you know, is pi r square h. What is volume? 128 pi. 128 pi equal to pi r square h, where both r and h are variables. So from here, I can write h is equal to 128 by r square. So I've expressed h in terms of r. So now this is what I need to minimize. It's a function of r and h, two variables. How do I write one variable in terms of the other? Use the data that is given. Volume is pi r square h. Volume is 128 pi. So 128 pi equal to pi r square h. So h is equal to 128 by r square. Now we will substitute in s. Now s is equal to 2 pi r into h. H is what? 128 by r square plus 2 pi r square. So now it has been expressed as a function of a single variable, namely the radius of the cylinder, or the radius of the cylinder. Okay, this is for the 2 into 128, 256 pi by 1 r will get cancelled. So giving you 1 r in the denominator plus 2 pi r square. Now ds by dr will be 256 pi. What is derivative of 1 by r? R power minus 1. So minus r to the power minus 2. So minus 1 by r square plus derivative of 2 pi r square will be 4 pi r. 2 pi, keep it as it is. If you differentiate r square, you get 2r. Now to find the critical point, equate it to 0. Okay. So 4 pi r is equal to 256 pi by r square. Pi gets cancelled. So r is equal to 256 by 4, r cube is equal to 256 by 4. This is what? 6 4s are 24 and 4. So r cube is 64. So which means r is equal to 4 centimeter. So to find the critical point, we equating ds by dr to 0, from which we have found that at r equal to 4 gives you the critical point, that is ds by dr equal to 0. So at r equal to 4, we speculate that the surface area may be minimum. So how do we justify the second derivative test? Second derivative. So this is ds by dr. So what is d square s by dr square? Will be 256 pi. Okay. Now we have minus r to the power minus 2. If I differentiate, what will I get? I will get 2r to the power minus 3. So into 2 by r cube. Okay. Then the derivative of the next one will be what? 4 pi r. If I differentiate, I'll get 4 pi. Okay. Now, this is 256 pi by, what is r cube? R cube is 64. R cube is 64. 256 pi into 2 plus 4 pi. So this is 2 goes 32 times. Anyway, you can simplify this. You can easily see it is greater than 0. 256 pi by 32. You can simplify. So this is 864, 8 times. So 8 pi plus 4 pi, which is 12 pi. So the second derivative is 12 pi, which is greater than 0. Therefore, if the second derivative is positive, then it is minimum. Therefore, V is minimum. That is, sorry, the total surface area is minimum when R equal to 4 centimeter. How have we justified this? We have also found the second derivative. The second derivative is positive, which means that surface area is minimum at R equal to 4 centimeter. Is it clear? Show that the right circular cylinder open at the top and of given surface area and maximum volume is such that its height is equal to the radius of the base. So what is given, or rather what is fixed? Given is you have a right circular cylinder which is open at the top. Okay, and given surface area. So surface area is fixed. It's a constant. Fixed means what? It's a constant. So let this be R, let this be H. So 2, what is that? It's open at the top. So 2 pi RH is the lateral surface area. Plus only bottom is there. So 1 pi r square. This is fixed. Constant. Okay. Now what is it that you need to maximize? You have to maximize the volume. Volume is, pi r square h. In fact, you have to prove when V is maximum, we'll call this as V. Okay. When V is maximum, then height is equal to the radius of the base. That is h is equal to r. We have to prove h is equal to r when V is maximum. Now, it is a function of two variables. R and H are variables. So, we need to express one in terms of the other. How will you express? Using the given information. So, from this, it's easier to express H. S is a constant. S minus pi r square by 2 pi r is your H. Now, volume is equal to pi r square into S minus pi r square divided by 2 pi r. Okay, now pi and pi gets cancelled. 1 r gets cancelled. Okay, so we are left now with B equal to r into S minus pi r square. Is there anything else which is left? R got cancelled, pi got cancelled, only 2 is there. So I can take that outside. So V equal to S by 2 R minus pi by 2 R cube. So I have expressed V as a function of a single variable, namely R. What is R? The radius of the cylinder. Now dV by dr will be equal to, differentiating it with respect to r, because r is the variable, s is a constant, you will get s by 2 minus pi by 2 Differentiating this will give you 3r square equal to 0. To find the critical point, equate the first derivative to 0. Okay, so I will get s is equal to 3 pi r square. Why? Because 2 and 2 will get cancelled. So s is equal to 3 pi r square. If s is equal, we want to find what is it that we need to prove. When the volume is maximum, we are speculating that the volume is going to be maximum when s is 3 pi r square. Okay, then what is the relation between h and r? You substitute in 1. Substituting in 1, you get h is equal to, what is s? S is 3 pi r square minus pi r square by 2 pi r. 2 pi r square by 2 pi r, which is r. So we have proved h is equal to r. We are speculating that at this critical point, okay, the height should be radius. We have proved that, but we have to confirm it using the second derivative. So what is the second derivative? So dv by dr, you know, is equal to what? S by 2 minus 3 pi r square minus 3 by 2, 3 pi by 2 r square. D square v by dr square, this is a constant, so 0 minus, okay, r square, 3 pi, you keep it as it is by 2, differentiating r square, you get 2r. So you get minus 3 pi r, which is less than 0. So V is maximum when H is equal to. So V is maximum, volume is maximum when height is equal to R. So what is the difference between this problem and the earlier problem? The earlier problem we maximized, given the volume, we maximize the surface area. In this problem, given that surface area is a constant, we found that cylinder open at the top which has got maximum volume. So we proved that when H is equal to R, it will have maximum volume. So I hope that this session was useful. We were able to do 3 problems, but I am sure that with the slow discussion that we had, that you would have understood, and you have now would have got understood the algorithm behind how to solve these problems, like identifying the constant and the variable, relating the writing the function that you need to maximize or minimize as a function of a single variable using the given data, and finally finding the critical point, and then finally using the second derivative test to confirm whether it is maximum or minimum. Okay. All the very best for your, I'm sure your first term exams will be approaching. All the very best for your preparation. Please go through these problems, try them on your own, and you can look into the video for confirming whether your solution is right. Until we meet next time, thank you. If you find the session useful, please share it with your friends.